I'm Sean Waltman, lead our cloud geography team. And as George mentioned, segmentation is the next topic that we wanted to go over. That tiny URL will give you these slides, so I'll give you a couple seconds to grab them. It's tiny.cc/ee-se-dublin. All right, so on the right-hand side of the screen, this is actually a screenshot from OpenET about the transpiration project. And you can clearly see distinct objects here, right? These distinct fields with very clean polygons, whether they're the center pivot irrigation fields or some of these other fields. And so I wanted to start just by talking a little bit about segmentation and remote sensing and why we do it. A couple of reasons. One is that when you look at those types of maps, you can, as a person, you see these edges, you see these boundaries, and there's these distinct things. And some of those distinct things for agriculture are fields. And if you're trying to calculate yield, it's extremely important to have an accurate boundary so that when you're counting the pixels that go into your equations, you're accurately measuring how much yield is coming off of that particular field. So if you're working with customers that are in commodity trading or folks that are producers, they're going to want to have this. And sometimes when you're a producer, you might have that data, right? If it's your farm and it's your field, you may have driven your tractor around it, and today's tractors have GPSs on it, and you get these hyper accurate, corrected GPS positions. But if you're looking at commodities across, an entire continent that you're trying to make billion-dollar trading decisions on, you don't own those fields, so you have to get them somehow because you want to measure something. The other use cases are you actually see an object, and maybe it's not a field, maybe it's a building, maybe it's an F-15, and you want to be able to extract those things and create polygons out of them, or you want to classify them. The example there is showing some ships in a naval yard. So how do we typically do this, right? How do you do this if you were a customer that wanted to have these segmented fields so that you can do all these analyses? One way is you could just buy them. All right, there are companies out there that offer this as a solution, and George always recommends Digifarm. They don't have complete coverage, but where they do have coverage, they're very, very good. So that is an option, right? Don't even bother with everything we're going to talk about today. Just go out and buy it. Another approach, this is from Nesri blog in February, is to hire college students. In this example, they sat down and they had these map hackathons, and it says that machine learning they didn't think was really there yet, so they were going to do this the old-fashioned way. And they got students volunteered to digitize 3,000 fields in 2 hours. So I guess at the rate of about 1,000 fields per pizza, this is another good approach to segment fields. And they were just going to literally hands up digitize these. Or you could use, if you look at Earth Engine, some of the examples that we have, like the center pivot irrigation, there's image and pixel-based processing approaches. So this is a convolutional method where you go through and you compare square kernels to round kernels, and you find the differences, and you're able to find the edges that way. And that works really well for things like center pivot irrigation, right, that are actually laid out with a set diameter so that they make it a little bit easier to detect. Or you go and talk to Genna or Noel, and you talk about things like SNCC. And one of the inspirations for this was Noel gave a great talk this was across the street back in 2018, looking at how do we do this? How do we do this segmentation and moving from a pixel-based approach to an object-based approach there. There's a link in here to go take a look at the algorithm of SNCC that's in there. But there's challenges, right? There's challenges in there that you may be aware of that Noel's talked about. But that is an approach as well, and it does yield good results. But for today's session, we are going to do something very different, very modern, and that is to take advantage of some of the cutting edge ML transformers that are emerged in the last year, right? So if this image doesn't look familiar to you, a model from Meta called segmentEverything that uses visual transformers, but we're going to put that together with Earth Engine and Dataflow to see what we can actually segment. A little bit about segmentEverything. So this was based on a now open image data set. They went around and collected photographs, not just from Meta users, but also they contracted this. And it is a 10 million photo library. It's an open library. And on that, they created 1 billion masks. right? So they basically built up this library of six times larger volume of images than was previously available in the open domain, and now 400 times more masks. So basically, this was the training data set that Meta went out and built as part of this process. And then they took the idea of a vision transformer. So if you've been paying attention to the AI revolution that's happening right now, transformers that Google first developed about 4 or 5 years ago have become the foundations for ChatGPT and for Bard and for all these things that you're seeing. And the idea here is that by training these models based on all of those images and those masks, you're able to do encoding, most of the time leveraging a GPU, but you can also do it in some CPUs, push it through a number of layers for embedding, and then this prompt thing, right? Being able to supply something that the transformers are able to create connections between objects. And so we're going to come back to the prompt piece because that actually is going to lead to the what's next phase of this talk. But just keep that in mind, is that the ability to come in here and have that prompt as an input is going to be very important. And if you're not familiar with a prompt, it's the same thing like when you're using ChatGPT or you're using Stable Diffusion and you say, I want a photorealistic picture of the Earth Engine training team or the logo in pastels or something like that. And the transformer takes all those objects, understands what you're trying to say, and then assembles that or imagines what that could be. So very quickly after this came out, Xusheng, who's one of our Google developer experts for Earth Engine, said, hey, this is great, but this is a problem in remote sensing, and very quickly started working on a package called Segment Geospatial. So it was take segmentEverything and apply it to aerial imagery. His approach is really like the inspiration for this, but what he did was look at it very much from like a interactive notebook example, like prove that it could work, but not do it at scale. And in this example, they actually go and they scrape a bunch of tile servers to pull down high resolution imagery, but you can kind of see those results, right? Like we're starting to see things like the baseball field, the diamond being segmented, et cetera. So this is pretty exciting. One of our teammates, Brady Allred, worked really quickly to take that and bring in a notebook example for compute pixels. So basically using the REST API to stream data into a Python notebook, assemble a NumPy array image in the notebook, and looked at an area and said, hey, this is pretty good for fields. And so those two things about a month and a half ago led me to say, hey, we've got this event coming up in Dublin. We want to talk about agriculture. This would be a really cool opportunity to figure out what it would take to take that concept and scale it up. So let's segment Iowa. And why did I pick Iowa? I'm from New Jersey. It has nothing. My grandfather did go there and was a Hawkeye. But other than that, there was one reason, and the reason was unlike the Central Valley of California, there's a lot of corn in Iowa, right? So when I look at some of the stuff that George is showing, it almost felt like cheating because it was like, well, there's such distinct things, right? So I wanted to see how this would perform in an area where everything kind of looks the same. And to prove that point, what I started with, I wanted to go as high res as possible. This is planet imagery. Okay, so this is a bi-weekly product, a base map product from Planet. And this is 2022. And this is looking at a quality mosaic. So this is a greenest pixel mosaic for the Midwest, for the entire Corn Belt, essentially. And if you look at it here, it looks like Google Earth, and there's really not that much that you can really pull out. Everything is green, right? And you zoom in further, everything is green. Everything that you drive other than the streets is green. Well, if you go through and do what George just did, right, and create an HSV version of this where we're looking at the phonology and you're fitting this to a harmonic, it starts to look a lot different, right? And now I can clearly see that, yes, there's green, but some of that is probably trees that are green all year, right? Things that are not crops that are along the river. And this color difference is telling me that, this is a corn planted at slightly different dates, but you can still see like the fields much more distinctly than if you were just looking at all of this green. And the whole idea with that, my hypothesis was that segmentEverything would want to have a little bit more distinction, a little bit more difference between all these different features, and would probably produce a better result. So this is nowhere near as complicated or accurate as the harmonics that George was talking about. You can see that the fit isn't even all that great, and this is only, I think, like 12 to 14 weeks of imagery, right? This is just the growing season. So if you went back over time and you'd be able to bring in some of George's techniques, you'd probably be able to tease this out a little bit better and get an even better distinction between some of these fields. But it's really neat when you zoom back out. You can really start to see that corn belt, right? Like if we're assuming that red is likely corn, and maybe a little bit of soy mixed in there with some of the other colors. When you start to look at this region, now that's a lot more for you to comprehend about what the scale of this problem is. So how are we going to approach this? Well, right now, segmentEverything is a PyTorch model, right? Cloud AI Platform Connector for Earth Engine does not allow you to run anything other than TensorFlow. So being meta and being a PyTorch-based model, right now our option is to basically export this and then run it in a operating system that can support PyTorch and do that at scale. So this is a covering grid of Iowa. This is an approximation. This is not to scale. But the idea was to basically just export this into as many geotiffs as we could and find the right size geotiff for this model to process. I will say that one of the next steps is to be able to do this with the Vertex connector that we've been talking about, right? So we could actually do this interactively with a PyTorch model running in Vertex, and then also do it at batch once we kind of are happy with that. And we can use Vertex AI scaling, but we're still a couple of months away from that being a reality. Okay, so the other thing to note is that segmentEverything was not designed for remote sensing, right? And it really has some limitations. It has no concept of multispectral. And so that model could probably be a lot better. And maybe a better approach is to actually go and train that model with multispectral imagery, right? More than just 3 bands. But for today, segmentEverything is just looking for RGB images, and specifically it's looking for 8-bit images. So the first step, and I found this only because I had already exported it just as floating point data, was to actually convert those images before the export to 8-bit. And that's very simple. You just basically, there's a line of code there to make basically put it into 8-bit and then export that to a bucket. Projection wise doesn't really matter because the segmentEverything model, segment geospatial package is using raster IO and proj4, so we can read any projection, but 4326 was kind of a good default for me, and then just pump that out into a bucket. I mentioned the size. So this file dimensions parameter that's there, 1024 by 1024, turned out to be kind of a good fit for a couple of reasons. One, if you just let Earth Engine, if you just give the region of Iowa and you export Iowa, Earth Engine's going to take that size and it's going to automatically figure out how big of a geotiff it can write. It's going to try to minimize the number of files, which a lot of times is good, right? You don't want to have so many files. But when you're trying to load this into GPU memory, there's limits in terms of how much your machine can actually load into memory. So 1024 seemed like a sweet spot. The other piece of it is that if you went much smaller, then you're starting to break up the fields into smaller chunks and you're losing some of the context. So I played around with 1024 and 2048, but ended up settling on 1024. The result of that, though, Earth Engine's really fast. It's great. You want all of Iowa, this 8-bit image. About 2 hours later, it pumped out over 26,000 geotiffs, right? So now we have a problem of, well, that's a lot of individual files that we have to worry about. And when you run segmentEverything, we'll talk a little bit about the differences between CPU and GPU. But if you don't connect, if you can try running this in Colab, if you don't get a GPU in your runtime, you can count on about 8 to 12 minutes per image for a CPU. With a GPU, that goes down to about 12 seconds. So I don't know if this is actually available to everybody, but in my collab anyway, I have the ability to pick a GPU. So I think that's fairly new. But what you want to do if you want to play around with this, like as I was starting to do my experiment, was to set up a notebook and make sure that you got that GPU resource. And one that comes by default is a T4. I understand that we have a ability to pay to get more of these. This is just the free collab, but in the paid version, you're able to reserve larger clusters of GPUs. And you can verify that you actually have a GPU by opening up the resources tab, and you should see this GPU RAM. So each one of these Tesla 4 NVIDIA GPUs has about 15 gigabytes of RAM. And when you're working with PyTorch or when you're working with Python, you really want to make sure that you actually have that GPU and the drivers and you're able to utilize it. So a way to do that is just to import the Torch library and then load up an image and then just check to see this CUDA is available. So Colab makes this somewhat easy for you. Right, Colab will actually, behind the scenes, make sure that the runtime has those NVIDIA CUDA drivers, which are not open source, but there's a way to install them, and Colab kind of takes care of all of that for you. So the next piece here with Segment Geospatial, this is that first image. So this is just the very top northwest image. So I load that in there and I put it onto Leaflet. I will say with the Segment Geospatial package, similar to GE Map, there are a ton of dependencies that are complete overkill for what we're doing, because Xusheng is more interested in building this as a full leaflet experience and interactive. And really what Segment Geospatial, all it really needs to do is it's running the SAM model, and then it's putting, which is just using XY coordinates of the image pixels. He's just reading the geotiff, and that's very important for us because we want to keep the spatial context of this image. Everything else in this package is fairly useless to us. So it's big and it's bloated, and it's not a knock on or anything, but it's more than what we need for this particular use case. So anyway, so we load up this first image, and now what we're going to do is try to segment it. So that works by running defining the SAM geo method. And one of the things you need for it is a checkpoint. If you've ever run anything in PyTorch or TensorFlow, running on a GPU, you may, if you maybe been making deep fakes at home, I don't know. You've gone through this process where you provide training data, and then you provide labeled data and you're testing it, and you're running through basically to the point where you're getting diminishing returns. And that becomes this checkpoint file. So Facebook makes this file available. It's a visual transformer. It's model H. There are some options. There's like 2 other models that you can use as well, but this is the one that everyone seems to think is the best performing, but it's large. So this one is almost 3 gigabytes. And so the first time you run this, it will download this checkpoint and put it into your Torch working directory. And that's going to be important as we move forward, because you need this, and this file is large. You download it, you have to put it into your GPU memory, and it has to sit there in addition to whatever it is that you're trying to infer against. Okay, so you have to download this checkpoint, and the package does that for you, but it is large. Okay, so then when you actually have the model and you've got all your arguments set, the next step is to then actually try to do the inference. And you can watch this happen when you click off this process in the Colab notebook. Your GPU RAM will start to peg. If I'm running a 1024, I was getting to about 7, about half of my RAM. If I went larger, I was getting to that point where it might get too close and crash the GPU. So that's one of the limitations. So what were the results of that? So this is our first image, and here's what it segmented. Right, so that was pretty promising, right? You can see those fields. You can see that they're clearly turning into these, randomly stylized polygons, and so that kind of led me down the path to say, yeah, this is probably going to work. How do I now scale this up? So my go-to when it comes to this type of, I've got 26,000 images and I want to process them, is to go with Dataflow. If you want to follow along at home, Segment Everything is now published, and so you can grab this, you can check this out as we walk through it. But basically, this is a custom Dataflow pipeline and custom container for running this at scale. So Dataflow is in our processing family. It is an ETL tool, right? Extract, transform, load. And the whole idea of it is it is based on Apache Beam, open source project that Google is a heavy contributor to, and Dataflow is our managed service, right? One of the things that Google Cloud does extraordinarily well is that we contribute to open source technology. This is a great example of it, and then we run the best-in-class managed service for that particular service. But the whole idea is that it's reading some input data, doing some operation, producing some result, and then that's your pipeline. Dataflow supports two modes of operation. You can leave Dataflow running, and if you've got streaming GPS data or something that you want to constantly process, you can stream that data in, or it operates in batch mode. And for us, our input is basically batch, right? It's a static set of 26,000 files, and it's going to go into a not always running, I'll show you some of the costs associated here, Dataflow pipeline. And then our outputs, or our sinks, are designed to be cloud storage, BigQuery, and Earth Engine. As of right now, our output is cloud storage because I didn't finish this entirely. But the idea would be this would be a perfect thing to push into BigQuery or into Earth Engine. And then the into Earth Engine piece is fairly straightforward. Without that connector, it's enticing, but not exactly useful to push that data into BigQuery at this time. Okay, when you talk about Dataflow, the core of it is running this pipeline. And so your pipeline is basically this beam transformation that you've laid out. And we'll walk through a couple of different steps. This input leads to this process leads to this process leads to that, and you're basically laying out a pipeline. So you typically kick that off from just a cloud shell or from a virtual machine. You want to always make sure, one of the requirements is that the caller has the same dependencies and versions of Python. And this starts to get pretty tricky to try to make sure that they're always matched. So we'll talk a little bit about that. Then Dataflow provides a monitoring UI where you can see how this is progressing. You can see the worker logs. I highly recommend, and you'll see in my code for the segmentEverything.py, a lot of logging.info, because you want to be as verbose as possible, because this thing will just sit there. You don't know what it's doing. So the more logging you put in there, the better. And then it goes to this fully managed service. And Dataflow basically just looks at the pipeline. It looks at the rates at which you're running the pipeline, and it auto scales based on that, in theory. There are some problems there that we'll get to in terms of quotas that might stop you from actually auto scaling. But in our case, we made this a little bit more complicated, because typically I don't care too much about the container that actually runs, or the worker that actually runs my Dataflow pipeline, right? I don't care what operating system it's running on. The hardest thing that I've ever had to do prior to this was making sure that the dependencies, the Python dependencies, were there. And that's basically just, making sure that you're versioning your requirements.txt so that, if you've worked in Python, you know what it's like to try to make sure that dependencies don't conflict with the version of Python that you're running, with the operating system, and within each other. So basically, it's a pretty simple approach. But for us, we had to make sure that those workers have GPUs, right? It's not Colab. I can't go in there and make sure and define that in a nice UI. The next piece is that those workers have to download those proprietary drivers. Right, so that in itself is a process. Then by default, the Dataflow workers were running Python 3.7, and Segment Anything needs it to be at least 3.8 to run. And the next piece was that every single worker needs to have that checkpoint. And if you think about how Dataflow works, when you find the job, it goes and builds a worker, right? And say you wanted to scale to 32 workers. If you don't have that checkpoint, every single one of those workers, as they come up, the first thing it needs to do is go download a 3 GB file. right? So not only is that time consuming, but I'm sure at some point Meta is going to be like, wow, why are these people downloading, 60 gigs of our data every time they run this job? And the other piece is that the model itself is still very memory intensive. So looking at what we have across our fleet, there are very, very expensive A100s, super high in RAM. They're the newest and the best. But we have this low latency, low cost, fairly affordable fleet of T4s across many of our data centers. So for me, it was a pretty obvious choice. This supported CUDA, it worked, and it was not like exorbitantly expensive. So running on the T4 was the choice that I made. But it is very difficult still to get these, okay? The entire pipeline ended up taking me a lot longer to run because I was denied my quota uplift request. I was told that the Google Geo billing account was not at a high enough level of trust, our internal billing account, to get this quota. So if you're planning on doing this, start a little early. Make sure that you get your allocation, because ultimately I was bound by the number of GPUs that I was able to get in a particular region, and it was 4. Okay. Again, it tells me that that he's got 8 from his Colab free version or something like that. So I don't know what to tell you, but that's something that you really have to keep in mind. So all of those things mean that I couldn't just do what I typically do and just not worry about the worker. And so I'm not a Docker person. Like, this is fairly new to me. So there was a lot of trial and error to try to figure out that in order to make this work, I really had to get specific about what that worker looked like. Okay, so that means that we had to use custom containers. And the last time I went down the path of using custom containers, it was custom, but you could only pick from like these 5 custom containers. So Dataflow has evolved in the last year and a half, and now custom is fairly open, and you really can define what that worker looks like. And okay, fine. So if I did this, if I had this custom container, I could assure a couple of things. We needed to have our worker to have GPUs. I needed our worker to be greater than 3.7. So with the custom container, I can define which OS and Python version that I want, which is actually pretty useful. I can pre-install all the requirements. When you install segmentEverything or segmentEverything, it takes probably 5 minutes of startup time just to download the dependencies and install it. And then I can also make sure that the CUDA drivers are there, right? So I can make sure that is all in place. And then I also make sure that I actually bake in that checkpoint into the container image. So rather than having like a 2 or 3 gigabyte container image, now I have a 7 gigabyte container image, but when that container starts up, it doesn't have to go download that data. So I don't have that download time. Okay. So basically what's going to happen is that the pipeline is going to call for a worker like it typically does. And that worker is going to go take a look at the pipeline instructions that tells me what kind of machine type, what kind of disk size, where do I want to run it, etc. Then it's going to go and grab my image. One of the parameters I'm going to pass to it is go grab my image from Google Container Registry and use that as the foundation of this particular worker. And the final step is to make sure that you grab a GPU. And when all of these pieces come together, now we have a worker that can actually work on this particular task. Okay, so how does this work? If you've taken a look at the repository, there's a Docker file, and I want to just go through some of the important pieces of that Docker file, which basically defines what this worker is going to do. And I apologize, I cannot make that larger. The first is that we're going to start with an image that Google already went through all the turmoil to make sure that PyTorch works, right? So there's a PyTorch image in Docker Hub, specifically with the CUDA 11 runtime. So we've done a lot of the hard work for you by starting with a container image that already meets that requirement. The next piece is that even though I have a requirements.txt that says I want to install segment geospatial, it needs all types of things to actually build properly with pip. So basically it needs GCC, it needs all of this libgl and libext, all these different dependencies. So I'm starting with a known image, then I'm going to basically do system packages installation to make sure that when I go to build my requirements that they actually work. and then basically go and build everything that's in the requirements.txt. The next piece is basically an add, which says add this file, and that's the file that, if you go back to the notebook that it downloaded from Meta, which is the checkpoint, and put it into the Torch cache directory. The problem is that this does this as root, and when you go to run the worker, it doesn't have root permission, so you do have to make it, you probably don't need 777, but you do need to make it readable to that particular worker. In the requirements.txt, you need a couple of things. You need Google Cloud, you need Apache Beam, you need Segment Geospatial. I highly recommend tagging a version on a lot of these just to make sure that we've run into dependencies, and George was pulling his hair out this past week as well, I know. So then we also need Triton and Cython. Triton is a part of the Torch framework. Okay, so the next piece is I need to give my image a name. So I called mine segment everything minimal, and that's what it is if you pull it. And this is basically a YAML file that I did everything with the Cloud editor, Cloud Shell editor, and Cloud Shell. Basically, it's saying, great, take that Docker file and then publish it to gcr.io, which is Google Container Registry, which, by the way, is being deprecated apparently, and there's something new coming, but for right now, we're using Container Registry. And then basically store that image there. And that's going to be really important because Dataflow needs to know where to go pull that image. So this is going to set up where we're going to actually build it. And the result of this is you just do gcloud build submit, and then what config you want to use that build YAML. So you can do this right now if you've already pulled it. And it'll basically go and build segment everything minimal. And you can see the different versions. And basically it keeps a artifact of the different versions, which is really useful if you need to roll something back. Oh, I changed something, I can go back to a last working container. So pretty cool product. All right, any questions so far? No. Yes.
A spicy question.
Yes.
What's the budget? Like, how much do you expect this to cost?
Oh yes, we will cover that. Yes. How much did I expect it to cost? Oh, I didn't know. I didn't know if it would be, pennies, or Hank would get a call and our billing account would be in worse state. I didn't really know, but I figured I couldn't really spend that much. So looking through a couple of the pipeline arguments. So when you build a pipeline, a good library to use is argparse because it allows you to put in these different arguments, and Apache Beam requires a certain number of arguments. So the first ones that come in here are basically just the where and what's of what we need the workers to be. And so the first one is to set our project. This is where this pipeline is actually going to run. The next one is the region. And again, this is something that you could look at a cost factor here, right? There are certain regions that are more expensive, but it also, you have to make sure that the type of machine that you want to use is available in that region. And that might also be dependent on where you can get quota. You might go to your cloud rep and say, hey, I need 32 Tesla T4s. And they'll say, great, you can run that in US West. And you're like, oh, all my data is in US Central. It may just be where the availability is, right, for those particular resources. So that region basically determines where you're running. And the next piece is the machine type. This one actually cost me about a day and a half. The issue is that you don't just need GPU RAM. You need to be able to read that image and the checkpoint into system RAM to transfer it to the GPU RAM. So if you just went with a default standard machine or a high CPU machine that doesn't have enough RAM, basically you would have all the dependencies available. I was checking to make sure that CUDA was there. Everything was looking great. And the images were taking like 12 minutes a piece to run rather than 12 seconds. So it was because it couldn't actually load the image and the checkpoint into machine RAM to transfer it to the GPU. The next piece is the number of workers. I would love this number not to be 4. So this is how many GPUs you can have. The issue there is, again, bound by the number of GPUs that you have available. Then the type of disk. This was also really important. By default, it uses standard persistent disk. Much better performance if you use SSD. A little bit more cost, but definitely makes the pipeline run faster. And then the disk size. So thinking about what these workers have to do, they're going to get a list of 26,000 images, right, that they're going to have to download. And so You want enough space to make sure that even though we're doing garbage collection and cleaning up the data after we process it, things always bloat a little bit. So you can actually specify the disk size. So I'm going to take that 7 GB image. It's going to apply it to a 100 GB SSD, expand the file system, and now that worker's got 100 GB to work with. Finally, it's what's the container image that we want to run, and this is just the URL to your cloud registry for that particular container. The next piece is your input and outputs. So you want a source bucket. So where did Earth Engine export that? And if you put it into a folder, you can supply the folder. What type of files am I looking for? This is left over from a previous one where I was doing net CDFs and whatever. So I was looking at different types, but basically we're always going to be talking about TIFFs here. And then where do you want them to be written? All right, so I'm going to take them out of the Planet Harmonized 2022 1024, and I'm going to put it into this output folder, essentially. Simple stuff. This next piece also took me a really, really long time to figure out. These are all the extra things you have to tell Dataflow to actually make this all work. You have to basically do these Dataflow service options, which tells it to use a worker accelerator, and the type is NVIDIA Tesla T4, one of those, and install the NVIDIA drivers. So I mentioned that the drivers are already on the workers, but they're not installed. So this is a special Dataflow command that will actually install those drivers. It knows where to look for them because it has them from that CUDA image, and it actually will install the drivers. The next piece is this use runner v2. That's the piece that actually allows you to run a custom container. The next one, disable worker container image pre-pull. When you have a 7 gig, after about 5 GB on your container, Dataflow gets really cranky because it's expecting these things to be really, really fast to pull. And after 5 GB, for whatever reason, it will start canceling the workers because they're not responding fast enough. So if you put this in place, it gives them enough time to actually build. The next one, the number of worker harness threads, was probably the most painful. It should have been a little bit more obvious, but the issue was I mentioned that each GPU had 15 GB of RAM, okay? And I have 4 GPUs. Well, Dataflow looks at that and says, great, we've got 26,000 images, we've got 4 containers. I'm gonna give each container as much as it can handle. The problem is if they do it in parallel, after 2 images, your GPU is flooded, the memory is flooded. So this has to be done in serial on each worker, otherwise the GPU will crash. All right. Okay. Any questions on any of that? Cool. Hopefully that saves you some time when you go to do these types of things. It was a stressful week. I enjoyed it, but it was I would have rather done other things. So now let's talk about the pipeline itself. And what you see that image is actually the graph that you'll actually see in that workload monitor from Dataflow. And so a couple of different things to start about. This is the Beam pipeline. All right, we start by declaring P as our pipeline, and it's a pipeline with all those options that we just supplied in that input. All right, there's 3 main sections here: sources, converted, and converted segment object. That corresponds exactly to what you end up seeing in the graphic representation, okay? So the first one is sources, and sources end up gonna be something called a P collection or parallel collection. And all this is a list. Okay, it's a fancy list, God bless you. It's a fancy list that basically says use, you go and look at the GCS folder, get me a blobs, all the list of all the URLs of all the blobs, that's my input. Then the way that works is basically look at all the geotiffs and return a list of all the names. When you see this yield, okay, so it says for blob and blobs, yield this object back. What you're doing is, this is happening in parallel, similar to a MapReduce, right? We talked about that if you were in the beginner sessions yesterday. And so these are happening independently, and they're all being collected back as basically this collection. They call it a P collection. It's similar to a feature collection or an image collection. And then the next piece is to go and run this into converted. So I have this P collection. One of the neat things I can do with Beam with it is this par do or parallel do. So basically a for each for everything in that P collection. And then that with outputs tag allows me to yield information back to the pipeline. So basically all this is going to do, very, very straightforward, is download the GeoTIFF. Now, when you run your pipeline, you're running it from a Cloud Shell or from a VM. I typically use a VM just because I want to use tmux and I want to make sure that the pipeline stays up and running if I get disconnected. And basically, the Pardue is running on the worker. But the pipeline, it's all in the same Python script, but the Pardue is actually going to be what's processed on the worker. So it doesn't have access to global scoped variables or any other imports that you have, right? So think about it, it spins up in the world and then it has no idea really where it came from. So what you can actually do is put all your imports in the actual parallel function. That's a good optimization trick. So we do all those imports, then we download the blobs, we do a little bit of string formatting to rename them, and then we check to make sure and log that we actually have a GPU. And then we do everything that we did in the Python notebook. We generate a new TIFF, we give it an output, we generate masks, and we create a geo package. All right, so one of the functions, because again, sorry, we kind of went a little deep here. We want fields, we want polygons back, right? So segmentEverything creates an image. It creates a mask. And one of the nice things that Shusheng put in here was this TIFF to vector, and you can create a GeoJSON or a geo package. Geo package is a little bit better because it handles multi-polygons better than the GeoJSON implementation does. So I'm creating a vector version of this as well. So what it will output is in the geo package would just be a polygon and a value. Basically an 8-bit value. It can segment up to 255 things in a particular image, and each one of those is discrete for each tile. They don't necessarily mean anything. They'll be like polygon 5, but polygon 5 doesn't mean anything in the next tile either. So what I do here is just apply, give it a GUID to each one of those. Basically load this into a data frame. Give it a GUID, and also store the base name so that in the future, when I'm looking at this in Earth Engine, I have an idea of what image did this particular mask come from. Any questions on that? I know, yeah, sorry, Brad.
Making an attempt drawing those polygons which are artificially split the image.
Yes, that is that. Did I make any attempt? No. Did I know that was going to be a problem? Yes. And we'll talk about that. And Gen and I have been thinking about ways to approach that. But yeah, great. Absolutely. It's going to be a problem. Yep. Anything else? Yep.
In Google Functions, you have like this shared global namespace. So between each run, might just do some teardown steps, make sure that's not done. You have to do the same thing the workers in between?
No, there is I don't think I have it in here. There is a particular job name, and Dataflow appends that to the name of all the workers and then associates them with that job and then tears them all down. Yeah. Yep. Good question. Okay. So let's take a look at the results. So first of all, how long did it take and how much did it cost? So with my 4 GPUs, it took 2 days and 7 hours of wall time. This is something that it actually cost Google more to have me do it this way rather than giving me more GPUs for a shorter period of time, because I ended up keeping all those SSDs and all the CPUs spinning while this was happening for 2 days. But in actual vCPU time, that was over 1,700 hours of CPU. And the same for all the memory and everything else that I used. So it could have been a lot faster, should have been a lot faster, and it will be a lot faster if you get access to more GPUs. It generated over 18 million polygons, covering over 145,000 square kilometers. How much did it cost? So running all those machines, Dataflow has this nice little cost tab that'll show you all the costs. So it costs $140 to run this job over those 2 days and 7 hours. Whatever reason, Dataflow doesn't show you the GPU time. And I think it's because it's still early days and it's not with all the hoops that I had to jump through, it's not something that a lot of people, I guess, are doing at the time. So GPUs aren't shown, but you can go into the Billing Explorer and look at the particular GPU in the region that I ran it in, which was South Carolina. And that was an additional $97. So all in, we're like, $250, to run this job. Okay, so if you have the slides open, we can take a look at what this looks like. I didn't wire it all the way end to end. I had that CSV file, and then I just did a create asset from the CSV file. It's 18 million polygons, and so displaying that in Earth Engine could be a bit of a challenge, so I wanted to take advantage of feature views. I have some thinning issues here because it looks pretty sparse when you're zoomed out. But when you zoom in, that feature view performance really comes through. And I've got a couple of different layers here for you to look at. I've got the actual segmentation, but then I also have, whoops, I didn't even check that this morning. Okay, I got to look at why that looks so bad and fix that. But I've got basically what we started with, which is the histogram stretch. I'm sorry, the harmonic fitted input image, and then our segmentations. So pretty pleased with the results of this and the performance that it has. Now it's interesting, of course, when you're looking at it against what Google's imagery in there, it's going to be different than whatever Planet captured in 2022. We probably flew that imagery in 2021. So sometimes it'll match up perfectly, but you really get a good idea for how well it performed when you turn on the underlying imagery. And in a lot of cases, it did really cool things. Like it found this field and segmented that perfectly versus the house. And this is something that you see pretty common, where it's got the grass, and then there's farmer's house and the field that's there. It also segments the water bodies fairly well. A couple things that definitely could be cleaned up. If you look here along some of the edges, I've got a bunch of little tiny polylines. There are polygons. There are arguments that you can tune the model, right? You can tune the model to try to do some post-processing with OpenCV to remove smaller things, but we could also handle these in Earth Engine if they're below a certain threshold. We could filter them out. But all in all, really, really good. Now, Brad's question was a good one, and it's what are you going to do with all the tiles? And it's tough to tell where I've done everything randomized there. If I change this to value, again, each tile is going to have a value of 0 to 255. So this will actually kind of highlight the artificial borders of the tiles a little bit better. When you look at it like this, you'll have more clear indication of where you have tiles, right? So this is a tile, this is a tile. And what Brad was asking is like, what are you going to do about the fact that some of these things they're the same field, but they've been segmented differently because they're on a cross tile boundary? What's that? Yeah, so you could stitch the boundaries. You could have, those college students come through with a vector editor and just merge these things. But again,
because they're segmented based on, you want to know that it's barley and barley.
Right. Yeah. So you could look at things like, okay, so you look at maybe you do like a reduced region, come back in Earth Engine, and you do a reduced regions on some value. Get the mode of those two fields, and if they touch and they have, they're same crop, but we're not getting to classification yet. But if they have similar values and they're right next to each other and they have a shared border, like I think that's one approach to do it. There's also some windowing that you could potentially do as you do the inference itself, right? You could take each one of those images, stitch its 4 neighbors, and then you would have overlaps that you could then dissolve on top of each other. So there's a lot of things that you could potentially do there. But I mean, from an overall standpoint, like it does a great job, and I was to do 18 million across the entire state. It's a pretty good start. Now, when we go into classification later, one of the other things that you could do is just find all the stuff that's not your crop and get rid of that. So you could probably whittle this down to a closer approximation of exactly how many fields there are in Iowa. But this general approach should scale globally, right? And get you a pretty good result. So what's next? Like, what are the planned improvements? I mentioned in the very beginning, transformers and prompts, right? So what we did was completely unsupervised. I didn't tell it anything about what it was looking at. I gave it maybe a little bit of a help because I made it such high contrast between the different regions. But one of the things that you can do is provide foreground and background inputs. So here's an interactive example of doing that for this. I don't know if it's salt or sewage treatment. I don't know what it is. So basically, if you give it a little bit more information and say, actually, the red stuff is the field that I care about, and the green and blue stuff is people's houses and rivers and stuff that I don't care about, this is something to explore. Now, how would you do this in an automated way? My thought was to find these points using Pillow or something like that, to just give it a couple of color ranges that I'm interested in per image, read the image, and find points of each color type to provide to the model as inputs. So read each image, find 10 points that are red, find 10 points that are blue and green, and then pass that to the segmentEverything model. But again, transformers, AI, ML, we could do more than that. So one of the really neat things is you can bring in language LLMs, and you could put in something like tree, right? And without even having to provide examples of trees, you can use those LLMs to automatically say, I'm really interested in finding the trees here, or the F-15s or SU-27s or whatever it is, depending on what side you're on, that you're trying to find, and automatically do this segmentation with just that type of a text input. All right. Anything else? Great. Time for a break. Thank you all.